Today I am going to talk about demodulation in digital modulation schemes. So basically our subject of interest now is the demodulation of baseband and passband digital modulations. Let me yes, baseband and passband demodulation. Maybe we can add digital here, digital demodulation, right. So we will now come to demodulation. So far we have looked at all the possible or various possible ways in which we can put data onto a waveform for communication through a waveform channel, right. This modulation scheme could be a baseband modulation scheme or it could be a passband modulation scheme, depending on what kind of channel you are finally going to use. And so far we just looked at the mapping from data to waveforms. Now we like to go from waveforms which are finally being received at the other side and its conversion back to data, right. That is the job of the digital demodulator. Its function is precisely the opposite kind of mapping that the transmitter or modulator is doing for you. It's not, however, just an inverse mapping. You should appreciate that. Whereas the job of a modulator is comparatively simpler, because you have to have a pre-designed set of waveforms, pre-decided set of waveforms, and the modulator essentially carries out the implementation of a rule from data bits to choice of one of these waveforms, right. Unfortunately for the demodulator, you will not get one of these sent waveforms precisely in the same form in which it was sent. It will be received along with noise, distortion and other kinds of impairments, and therefore the job of a demodulator to carry out the so called inverse function, namely interpret a waveform into a sequence of binary bits, is a relatively non-trivial one as compared to the job of the modulator, which is a rather straightforward function, right. So basically a demodulator converts a received waveform which would be typically noisy. So I will say a received noisy waveform into a stream of symbols or bits. That is the basic job. So let me put it in the form of a picture really. If you have this demodulator, input is a noisy received waveform and output is stream of symbols or stream of bits. Okay. Now how well a demodulator is doing its job will be really therefore a demodulator, what we are talking about is how to judge whether you got a good demodulator or not so good a demodulator, right. The performance of a demodulator in a digital communication environment is really judged by its ability to give you very low error rates as low error rates as possible, what we call probability of error. So, what we would really like to have is low error rates when our received waveform is impaired by, so in the presence of channel impairments, various kinds of channel impairments. Okay. For example, these impairments could be noise, which we have talked about. It could be distortion. Your channel may introduce a lot of distortion in the transmitted waveform.
So how do you distinguish between noise and distortion?
I think the answer should be known to you by now. Distortion is a deterministic transformation of the waveform by the channel, depending on the restrictions that the channel imposes on it. For example, the channel may not support that particular waveform perfectly because of its bandwidth limitation. Its frequency response may not be flat in the bandwidth of interest, or its phase response may not be linear with respect to frequency in the bandwidth of interest. Any of these is a source of distortion. You not discussed channel distortion ever? You can have amplitude distortion, you can have phase distortion, and you can have nonlinear distortion, right? Amplitude distortion is caused by the fact that in the bandwidth of interest the channel does not have a flat frequency response. All right. Phase distortion is caused when you have a nonlinear phase with respect to frequency. If you have a linear phase, that will imply a constant delay of the input waveform to the channel output, right? If you have a nonlinear phase response, different frequency components are delayed by different amounts, and therefore the resulting output waveform is not the same as the input waveform. Okay. Similarly, you can have nonlinear distortion if there is a nonlinearity in the communication system somewhere. It may be in the transmitter, it may be in the channel, it may be in the receiver, right? That will cause creation of intermodulation terms. So you can have various kinds of distortions which are distinctly different from additive Gaussian noise or any kind of additive noise. Okay. So is it clear what is the difference between noise and distortion? They are two distinct kinds of phenomena. So in the presence of noise, distortion, or interference from other sources, distortion would include intersymbol interference. Intersymbol interference would come within the purview of distortion, right? Because after all, when you have, let's say you have a nonlinear phase response, right? That might cause what is called a spread of the signal along time, because different frequency components are coming at different time instants, right? I mean, they are coming with different delays, and therefore the received waveform may be perhaps a broader signal as compared with the incoming pulse. So as far as intersymbol interference is concerned, that effect is included in this term distortion. Now what I am talking about interference next is interference from other communication systems which are operating in the neighborhood of your frequencies, right? External interferences, which would be therefore somewhat similar to noise in the sense that they are also additive in nature. These other signals are also adding on to your transmitted signal, but they differ from noise in their statistical characteristics. Okay. Noise has a different kind of statistical characteristic, whereas another signal which somebody else is transmitting and is interfering in your signal will have a different kind of statistical characteristic. Okay. So these are the kinds of impairments that you may typically encounter in any communication environment, be it analog or be it digital, right? And as far as the digital demodulator is concerned, what we really like to have is a low error rate demodulator in the presence of all these impairments. Of course, for the time being, we will primarily concern ourselves with this impairment, that of additive noise, right? We will not really look into these other two impairments and their impact on the design of a demodulator at this stage. Maybe we will pass some comments here and there, but broadly we will be concerned with this most important channel impairment, namely that of noise. Alright. And our concern here will be to study some kind of optimum methods or as good methods as possible for demodulation. Okay. Now actually we have very well developed theoretical tools available to study the subject of optimum demodulation. These theoretical tools are studied typically in advanced courses of the kind which are known by the names of, let's say, things like detection theory or what mathematicians would like to call statistical hypothesis testing. And the primary idea there in this theory is to look at the answer to the question that your received waveform in the absence of noise would be one in every interval of interest would be one of many possible set of waveforms which are defined by the transmitter, right, which are defined by the modulator. For example, if you have an Emery modulation scheme, then you have a dictionary of m possible waveforms which could have been transmitted, and therefore one of these waveforms is being received in the presence of noise. A typical hypothesis testing approach to this problem would ask which of the m waveforms was most probably transmitted based on the received waveform that you have got. So given the particular received waveform that you have in a particular interval, which of the m hypothesis is true, namely whether the first waveform was transmitted or the second or the third or the mth. Alright. So that is a subject which is studied under these titles: detection theory, statistical hypothesis testing, and things like that. However, to take that approach, one has to go through a bit of formal background for which we don't have time. So we'll really look into, we'll take an approach which is slightly more simplistic and which embodies some of the very basic concepts in this, basic results in this, alright, which will try to motivate both mathematically as well as intuitively. So we'll take a slightly more simple and therefore slightly ad hoc approach, but it will still be quite satisfactory. I can assure you of that. The most basic principle that finally comes out of these theories is quite simple and concise, and essentially it is the principle of match filtering. Which is what we'll really study in detail now. Okay, and this provides the answer to demodulation of a very wide variety of digital modulation waveforms. So if we study the basic principles of match filtering, we will be well equipped to study optimum demodulation for digital modulations. Right. Just to complete my statement here, as I already said, we will primarily be looking at optimum demodulation in the presence of noise alone, right. Noise alone will be considered. One could pose the problems of optimum demodulation in the presence of noise and interference and distortion and all those things, right, which becomes obviously a more complex problem to study, and it is usually simpler to study them in a systematic step-by-step manner, and the first step always is to study without any other encumbrance, right, that is with noise alone. And one assumption that we will make here is that as far as the channel is concerned, it is not doing anything funny except adding noise. So it has sufficient bandwidth so that whatever the transmitted signal it is reproduced faithfully except for the noise appearance, right? And therefore we can do demodulation of a waveform one symbol at a time, right? Because there is no channel impairment, there is no interference from one interval to the next interval, right? No intersymbol interference and no cross interference from other channels. All we have to therefore do is study demodulation of one symbol at a time, provided we know the starting point of a symbol and the ending point of a symbol, right? The waveform corresponding to one symbol interval. Of course, another assumption therefore that we have made here is that we have perfect synchronization between the timing synchronization between the transmitter and the receiver, so that we know every symbol perfectly, symbol duration perfectly, right? So a symbol by symbol approach, okay? And so the problem is considerably simplified if we make these assumptions, because all we are looking at is one symbol interval. In given one symbol interval, we know we are likely to get one of several possible waveforms, and we like to obtain some method for deciding which. And we will simplify the problem still further by trying to just look at a much simpler problem of detection of a signal, the presence of a signal in a given interval. Okay, so we'll say let's only look at the very simple problem in which an observation interval may have a signal or it may have only noise. Let's try to find a method by which we can detect the presence or absence of a signal. Then we'll try to generalize this to detecting the presence of one or more possible waveforms, the presence of this or that particular symbol. But to start with, let's look at the detection of simply presence or absence of a signal in a particular observation interval. It's a much simpler problem to look at. So that brings us really to the concept of match filter, and we'll study that in some detail now. We have been talking about it off and on at various places in the past, and I'll start by writing down a few assumptions regarding the signal and noise. So let's say we are transmitting a pulse or trying to receive a pulse of shape st with some amplitude scaling factor a, which is of finite energy. So AST is a finite energy pulse with energy E sub p. So it's a pulse of finite energy E sub p, where obviously E sub p would be equal to integral of or in the frequency domain right. In general, because we have seen that we can represent our various kinds of modulation schemes very conveniently using complex notation, in general we will permit this pulse shape to be complex. So it has a real part S sub r and an imaginary part S sub I, because we will be using complex notation. Now this pulse, when received, is contaminated by noise, right? So let's talk about that noise. We'll assume that the noise is white sense stationary or covariance stationary, right? White sense stationary or covariance stationary. You remember what that means? It's the same thing. It's a basically, if you remember the definition of white sense stationary, that's precisely the definition, right? That is, its covariance function depends only on tau, not individual time instance at which the two random variables have been sampled, right. If you look at expected value of nt1 into nt2, this is a function only of t1 minus t2 rather than separately of t1 and t2. That kind of a noise process or random process is called either Whitesand stationary or covariance stationary. Of course, the mean is constant or 0. So, in general, we can take the noise also to be a complex random process, complex valued random process, having a real part and an imaginary part, and we will assume, and it is a reasonable assumption, that both the real and imaginary parts, if they exist, have identical power spectra, identical power spectral density functions, right. Let us call them each NF, right. nRT as well as n sub IT both have power spectral density function which is the same. That is, the real and imaginary components have the same kind of spectral characteristics, power spectral characteristics. It is a fairly reasonable assumption for most kinds of noise encountered in real life. For example, the real and imaginary components might come in when you produce the, can you see, you must keep in mind the physical picture behind each of these complex signals. These are the kind of things that you might see on the quadrature channels after you have done the, let us say, down conversion of the incoming passband signal into a baseband representation, which would be a quadrature signal and may contain the in phase noise and the quadrature phase noise. And typically they will have identical characteristics, power spectral characteristics. We could also talk about the autocorrelation function of this process, and we will say, since they have identical power spectral characteristics, obviously they will have identical autocorrelation functions. Let us denote that by phi tau. So, this is the autocorrelation function, this is the power spectral density function for each of these two components. So, if phi tau is the autocorrelation function of this or this, what will be the autocorrelation function of this noise process? Can you tell me? Exactly same or with some difference? Let us check quickly, write it. The mathematical definition is nt into n conjugate t plus tau, right? Alright. So, what will you get?
Two extra terms come 2j nRT into ni conjugate.
It is nr plus j.
Ni conjugate plus ni conjugate.
Okay, it is very simple to check that this will simply turn out to be 2 phi tau under the assumption that nr and ni are uncorrelated or independent. Right? Of course, uncorrelatedness would imply independence only under the assumption that nt is Gaussian, right? So, all those things. That is just to elaborate that I mentioned the fact that we will have to assume them to be either uncorrelated or independent, and uncorrelatedness of two random variables would imply independence of random variables if and only if the two random variables are Gaussian, and in this case it means if the noise process is Gaussian. So, that is a relationship between the complex noise autocorrelation function to individual components, right. So, if your noise was strictly real valued, its autocorrelation function would be phi tau. If it is complex valued, it will be 2 phi tau. That is only, a scaling factor will come to the picture. And similarly, the PSD of NT will be simply given by 2NF, right. And what is the relationship between NF and phi tau?
It's the Fourier transform.
They are Fourier transform pairs. That is your Wiener-Khinchin theorem. Okay. So, as I said, our immediate problem of interest is a relatively simpler one, that is, try to evolve a strategy to detect whether a received signal Vt which is a noisy version of the transmitted pulse AST, contains that pulse or contains only noise, right? Consists of a pulse in noise or noise alone. That is a problem, limited problem with which we will deal to start. That is, we are really doing is hypothesis testing with two possible hypotheses, right? Under this hypothesis, we are saying that our received signal, which we are denoting by Vt, consists of the pulse AST plus noise Nt, right? And under this hypothesis, Vt consists only of the noise Nt. The question is, which of these is true? All we have with us is observed waveform Vt. We want to go from this observed waveform over some interval, whatever, at the moment let me not specify an interval, but maybe infinite interval to start with. Let's say we are talking of detection of a single pulse occurring somewhere, right? And all we have is this Vt. We need to process it and finally produce a decision, right? Whether this or this is true. Now, if you were to take the proper mathematical approach, one would start just with this problem and the assumption that you already made, and nothing more than that. That is called a non-structural approach. That is, just start from the problem and the solution will itself tell you what is the structure of the processing that you have to do, structure of the processor that one has to finally adopt. But because we are not really equipped here with the tools of statistical hypothesis testing theories here or detection theory here, we will have to take a structural approach. And the structural approach starts by saying something about what kind of processor you will use, what kind of processing you will carry out, right? And the reasonable processing that comes to our mind, which of course can be shown to be optimum in using the non-structural approach, is that you will pass this signal. See, I have just illustrated here by a diagram here. This is your pulse, which is contaminated by some noise, and this is how it might become after contamination. So this is what you are observing, this Vt, the sum of this signal plus noise, some random noise waveform, right? And what the structure we are proposing here is that we will pass it through a filter which ideally should do what? Should pass the signal completely without attenuation and should reject the noise completely. But that is something that is going to be impossible to do, right? So at best what we will try to do is we will pass it through a filter and then sample the output of this, because all we have to do eventually is take a decision, right? We don't really need to look at a complete waveform. So we will pass it through a filter such that as much of noise as possible is rejected, whereas at a certain point in time, if we sample it, we should see a large contribution due to signal, and therefore we will sample it at that time and compare the value with the threshold at this time instant, and if that sample value exceeds the threshold, we will declare that the pulse was indeed present. If it does not exceed the threshold value, we will say it is absent, right?
The third graph is for sampled output, the third one.
What is your question?
The third graph is the sample output.
No, this is the output of the filter. This is the input to the filter. This is the output of the filter which you are sampling at t equal to t0.
So which you sample?
Right?
So the point at which we sample and to detect the greater than some minimum,
Yes.
it shall depend upon the nature of the signal and the pulse shape.
Yes.
I mean, if it is constant over the whole single length, then we can sample it any of the.
I'll tell you what that point typically will be. Suppose this pulse is of duration t, right? Typically this point t0, intuitively you should know it should be at a point by which you could have seen most of the signal,
Yeah, that is the
right?
moment was used.
Right? In fact, you should have observed most of the signal, in fact all of the signal. So ideally T0 should be greater than or equal to the duration of the signal. You should not try to sample it before the whole of the signal has tried to pass through this filter. So the sampling instance should be located beyond T, or at least the smallest value that you can choose is the duration itself equal to T. So it could be equal to T. If this is starting at 0 and ending at T, right, this is a basically something intuitively something similar to what we discussed long time ago, that basically the idea is to reject noise. One way of rejecting noise would be to integrate it out, right? No, we are not really doing integration here, we are doing something more general than integration. Integration is a very special kind of operation. We are not putting any constraint on what that operation here should be. We are allowing the filter to be as general as possible, right? Integration will turn out to be a very special operation, but roughly yes, you can see it from that point of view, that you want to integrate the noise out over the symbol duration, over the pulse duration. So you should observe the pulse after you have done that for the whole pulse duration, and if you have integrated that out over the pulse duration, at the end of the integration interval you will probably expect to see a peak building up at the output of the integrator after the simple duration, right? And therefore that's the right point to sample it and try to take a decision, make a decision. So that's the basic philosophy of what is called a linear structure that we are going to use here, comprising of a filter which will try to optimize and determine. Strictly speaking, I should have shown a sampler here which samples the output of this at t equal to T0, which I have just written here, and then compares this sample output with a threshold which is somehow pre-calculated, and that produces a decision yes or no, whether the signal is present in this interval or is absent.
So then
Yes.
the output of this filter ideally,
Yes.
will it be identical to the original pulse shape? Or
In general it will not be. In general it will not be. In fact, pulse shape is of no concern to us,
Yeah.
right? In fact, I have shown that here. This is your input pulse. The output pulse will obviously a convolution of this, and it's going to be different from the input pulse. That is not also of any concern to us. All we want to is convert this into a value which you are going to sample, which you are going to obtain by sampling, such that it helps us to make our decision as correctly as possible.
Distinguishing between the waveforms will do later. So correlation, up till now that's not done.
Just yes or no, yeah.
Right.
Just
At the
yes or
moment
no.
we just want to produce whether pulse signal is present or well. Generalization to distinguishing between two signals or more signals is not going to be very difficult. I can assure you that once you have understood this basic concept. Okay. Any questions regarding this? So this is the broad framework in which we are going to work, and our concern is to look at this filter GT.
So the filter is matched to what? I mean, what are you going to match it?
We'll see that. That's what precisely we are eventually leading to. So let us see how we can go about it. What we'll try to do is we'll try to understand with this kind of input, which contains a signal plus noise, what kind of output we are going to get, particularly at some pre-chosen sampling instant, because ultimately the behavior of this receiver is going to depend on not really this output waveform, but on the nature of this value. How much of this value has been contributed by the signal, the pulse, and how much of it by noise. If for example there was no noise, this value will be completely contributed by the signal alone, right? But the presence of noise would disturb the value that you would have seen if signal alone had contributed. It might decrease it, or it might increase it, the presence of noise. It will perturb the ideal value, right? And depending on the magnitude of noise, that perturbation may be quite large, right? So basically what we like to do is design a filter such that the signal output, signal contribution becomes as large as possible but the noise perturbation remains
No.
as small as possible, right? That is how we will choose this GT,
GT.
right? The filter GT should be selected so that at this point most of the contribution is coming from the signal with possibly a small perturbation coming from noise. And if we can maximize the signal contribution to noise perturbation ratio, right, then we will have done a good job and we can hope to make a reasonably reliable decision. Is it fine? So therefore, let us look at the nature of the contribution here due to the signal and due to the noise, alright, and that will help us in designing the filter GT. Let us look at the output of the filter. Whose impulse response is GT and input is AST plus NT, right. Let us denote the output by UT. It will be convolution of the filter impulse response with the input, which is AST plus NT. So it will become A into ST minus zeta plus N T minus zeta d zeta. Alright. Now, is that fine? It is simply the convolution of your input. There should be a bracket here. Convolution of this input with the impulse response. Okay. Since we have a random process in the input, namely this noise process, this UT therefore is actually a random signal, like I illustrated here, right. This is a realization of a random waveform, right. However, what is really important to us is the mean value of the signal here, because different noise and some noise waveforms will cause different output waveforms, and when we are trying to do optimization, we like to optimize on the basis of average properties, right. So we will really like to look at the nature of this random process in terms of its mean and variance at the sampling instant, right. Let us look at what the mean value is and what the variance is. The variance will represent the perturbation over the mean value, and hopefully the mean value would be a contribution of the signal alone, right. In fact, we can see that very easily now. So first let us look at, let me just introduce some notation. The mean value of UT I am going to denote by some A times RT. It is just a notation, right, and variance of UT, variance of real part of UT is going to be dictated by sigma square, either a real part or imaginary part, because if you remember, NT is in general complex with identical variance for real and imaginary parts. Similarly, U in general is a complex random process, will have identical variances for real and imaginary parts.
So because the signal, the imaginary part of signal may not be equal to the real part, so we cannot say.
As far as the variances are concerned, it doesn't matter.
So how do you say that they are identical variances?
They may not necessarily have identical.
Okay, it's more or less obvious. I don't know whether it needs any explanation, because as we will soon see, the mean is really governed by the signal, because we are going to assume here, this is a very reasonable, at least a convenient assumption, and one can always enforce this kind of an assumption, that NT noise is a zero mean process, right. If this is a zero mean process, this mean value of this is going to be really dictated by the first term, right, and the variance is, this is not going to contribute to the variance. Variance is always around the mean, right.
Yeah.
The variance is going to be contributed by the noise.
So R is the convolution of G and S.
I am just calling it some RT. We will see soon see what RT is, right? Yes, basically that's what it is. You're right. Okay. So we are denoting the variance of the real and imaginary parts both by sigma square. Obviously, the variance of ut itself will be either sigma square or 2 sigma square, depending on whether it is real or it is complex. Okay. If ut is real, that is, if nt is real, then ut is real. That if you are assuming everything is real, then ut is a real process, real valued process, in which case the variance will be simply sigma square. If our everything is complex valued, then the variance will become 2 sigma square, as we have seen earlier. So variance of ut will be either sigma square or 2 sigma square, depending on whether it is real valued or complex valued. Okay. Now let's consider this quantity. What is the mean? These are the two important things: the mean value and the variance. Okay. Let's look at the mean value. Therefore, let's look at ART, which is by definition expected value of ut. Alright, from this integral, what can we say about it? If you take the expected value of an integral, we can,
take it inside
expectation is a linear operation. I can exchange it with the integration operation, take it inside the integral. The second term will become 0 because we assume this to be 0 mean. So essentially it will be, this is a constant. There is nothing random in this, right? So it will be simply integral of a g zeta st minus theta, and as Nikhil mentioned, essentially convolution of the input signal with the filter impulse response. Right? Now, out of this waveform, the value which is going to really matter to our performance is the value at the sampling instant t equal to t0, right? So we don't really need to look at this mean value for all values of time. We only need to look at the mean value of the sampling instant value, right? Now sampling instant is under our control, right? And if we are assuming that our pulse is sufficiently in the past, let's say somewhere less than t equal to 0, without any loss of generality, I'll assume actually this assumption is not really required, but slightly simplifies my analysis. It's not really required. We can assume t0 equal to 0, right? That is a sampling instant t0. I'm arbitrarily chosen, I'm calling that some instant 0, right? That has become my reference instant. Obviously the pulse would have occurred somewhere before that, right?
So this last expectation part is not very clear.
Yes, sir. How do you get this expression?
Because
Not clear?
The noise time will little bit thereafter.
The noise time is.
We are left with expected value of g zeta into st minus zeta.
Yeah.
Both are deterministic terms. There is nothing random. So the expected value of a constant is equal to the constant itself. I didn't think it was required in elaboration, therefore I didn't really elaborate. Is that okay? There is no random process here, so therefore it's a constant process, constant with respect to the random domain, right? There is nothing random in it, so it not constant with respect to time. It is a time varying function. Okay, can we come back to this point that it hardly matters what is the value of t0 I select, as long as I select it to be beyond the signal interval, right? So without any loss of generality, let me choose t0 equal to 0. That gives me your r t0 equal to r0. How can I obtain that? By putting t equal to 0 here, right? So that will become minus infinity g zeta s minus theta d zeta. Okay. Let me define this as some w zeta. Now, do you remember the Fourier transform properties? If I define w zeta to be this, what will be the Fourier transform of wf?
W star.
Star of it.
Conjugate of sf, right? Fourier transform of this is simply S conjugate f for a general complex signal. Alright. If you reverse the time axis, that's equivalent to conjugation in the frequency domain. Basic Fourier transform properties. Therefore, let's look at the implication of this property on this integral R0. Therefore, your R0, actually this is something I could have just told you intuitively, but let me just go through the whole thing, which is g zeta w zeta d zeta by Parseval's theorem. If we apply Parseval's theorem, what will you get?
Right now we're doing the conservation of G and S. So how do you get the frequency domain?
I am coming to frequency domain now.
We already
So far I have not come to frequency domain. It's all time domain.
okay.
G0 into W.
Right? I am coming to frequency domain now. Is that okay? So to come to frequency domain, I will just use the Parseval's theorem. This will become. Let me write A here also. A also here everywhere. And let me write mod square of this. The reason is because ultimately I am going to compare it with noise variance, right? So I am squaring it up and calling the signal output signal power just for the sake of comparison. Okay, so this will be the value, and by Parseval's theorem this will be simply, what will it be? Fourier transform of this into some star will come.
Star F.
Convoluted with SF divided
So
by
it will be
S.
star.
It will be a star F.
Star.
GFS convoluted
So S star F.
whole divided by S per integral.
I think there should be no. Oh, okay.
So we could have put T.
It is SF, not star F. Correct.
It is correct, but we have made the mistake.
Because it was W star.
Hmm?
No, sir, we have not made any.
WF is equal to S star F. So,
So twice you have taken the.
Star of star will be.
okay,
Yes, star of star.
right. That is how it
No
is.
mistake.
So this is the final answer, which I could have easily obtained directly, intuitively. How? Input is ST, whose Fourier transform is SF, right? Let me tell you a one line method of obtaining this result without having to go through all those steps. Input is SF, output is obviously this GF into SF, right? And the in time domain, the output is the inverse Fourier transform of this, which you are evaluating at t equal to 0, right? So that e to the power term becomes 1. So essentially you get this answer. Okay. So even without using Parseval's theorem, you can obtain this result just precisely in one line if you do things properly. Let's now look at the noise contribution. I think we'll stop here and look at the noise contribution and then compute the signal to noise ratio next time. Once we have got the signal to noise ratio expression, what we'll really do is choose a GT which maximizes that signal to noise ratio. such a maximizing SNR filter is what we call a matched filter. Okay, and we'll see what its form is.
So next